Since the earliest days of human history, the night sky has been more than just a backdrop of stars. It has been a mirror for our fears, our hopes, and our unanswered questions. Long before telescopes or equations existed, people looked upward and saw meaning in the darkness above them. To ancient civilizations, the stars were not distant suns or silent spheres of gas. They were symbols of power. Patterns in the sky became gods, constellations became stories, and the movement of the heavens was believed to guide the fate of humanity. The sky was not something to be measured, it was something to be respected, even feared. As centuries passed, myths slowly gave way to observation. Instruments replaced legends, and curiosity replaced worship. Science emerged not to destroy these ancient stories, but to challenge them, asking whether the universe followed rules that could be discovered rather than commands that must be obeyed. Step by step, humanity began to separate imagination from evidence. Yet the more we learned, the stranger the universe appeared. Instead of becoming simpler, the sky grew deeper and more complex. Each discovery revealed new layers of mystery, forcing us to question whether our ancestors were entirely wrong or simply speaking in a different language. Today, we stand at a crossroads between myth and mathematics. We can measure the age of the universe, track the movement of galaxies, and describe the shape of space itself. And still, one question remains unchanged from ancient times: is the universe a product of chance, or the result of a deeper design? In this story, we will follow humanity's long journey from myth to science, from divine narratives to mathematical laws. Along the way, we will encounter brilliant minds, unexpected mistakes, and discoveries so profound that they reshaped our understanding of reality itself. This is not just a story about the universe. It is a story about how humans have tried to understand their place within it. As scientific thinking advanced, it was expected to replace ancient beliefs entirely. Myths were seen as imaginative but inaccurate explanations, while science promised objective truth grounded in evidence and logic. For a time, this separation felt clean and final. The universe, once ruled by gods and symbols, now appeared to operate according to predictable laws. Yet an unexpected pattern began to emerge. As scientists looked deeper into the structure of reality, some discoveries began to resemble ideas that ancient cultures had expressed in symbolic form. Concepts such as order emerging from chaos, invisible forces shaping existence, and a universe governed by hidden balance appeared not only in old philosophies, but also in modern physics. What had once been dismissed as metaphor began to sound strangely familiar. This did not mean ancient myths were scientifically correct. Rather, it suggested that early humans were responding to the same fundamental questions that science now confronts using intuition instead of instruments. Where mythology spoke in stories, science spoke in equations. The language changed, but the curiosity remained. As research progressed, scientists encountered patterns that seemed finely structured. Physical constants appeared precisely tuned. Small changes in these values could lead to a universe unable to form stars, planets, or life. This raised difficult questions. Was this precision a coincidence, a necessity, or something else entirely? Some researchers argued that the universe is one of many, each with different rules, making our existence statistically inevitable. Others suggested that deeper principles remain undiscovered, waiting to explain this apparent balance. A few cautiously wondered whether the universe shows signs of intentional structure, not in a religious sense, but as a challenge to current understanding. Science did not return to myth, but it no longer dismissed wonder. The more knowledge expanded, the clearer it became that explanation does not eliminate mystery. Instead, it often deepens it. At this stage in human understanding, the universe was no longer seen as a simple machine, nor as a divine storybook. It became something more complex, a reality governed by laws, yet filled with unanswered questions that science itself continues to explore. At the beginning of the 20th century, physics faced a quiet crisis. Newton's laws had explained motion and gravity with remarkable accuracy for centuries, yet small inconsistencies were beginning to appear. Certain observations did not fit perfectly within the classical framework, hinting that something deeper was missing from humanity's understanding of space and time. Albert Einstein approached this problem from an unusual direction. Rather than asking how objects move through space, he asked what space itself truly is. In his theory of general relativity, gravity was no longer described as a force acting at a distance. Instead, it emerged as a consequence of mass and energy bending the fabric of space and time. This idea transformed reality at its most fundamental level. Space and time were no longer separate and absolute. They became dynamic, flexible, and responsive to the matter within them. Planets followed curved paths not because they were pulled by an invisible force, but because they were moving through a warped geometry created by massive objects like stars. The theory was radical, but it made precise predictions. One of them involved the orbit of Mercury, which had long puzzled astronomers. Classical physics could not fully explain its behavior. General relativity solved the problem with remarkable accuracy, offering strong evidence that Einstein's vision was correct. More importantly, the theory changed how the universe could be imagined. If space and time could bend, stretch, and curve, then the cosmos itself was no longer a fixed stage. It was an active participant in every physical process. The universe became something that could evolve, expand, or collapse depending on its contents. Einstein's work did more than correct equations. It reshaped humanity's perception of reality, revealing that the structure of the universe is far stranger and more elegant than previously imagined. From that moment forward, understanding the cosmos would require thinking not just about objects in space, but about space itself. When Einstein completed general relativity, the equations revealed something unexpected. Gravity, as described by his theory, could not support a universe that remained perfectly still. Matter would naturally pull inward, causing space itself to contract. According to the mathematics, a universe filled with matter should either be expanding or collapsing. At the time, this conclusion felt impossible. The prevailing belief among scientists was that the universe was eternal and unchanging on the largest scales. Stars might move, planets might orbit, but the cosmos as a whole was assumed to be stable. An evolving universe seemed too radical, too disruptive to established thought. To preserve this static vision, Einstein modified his own equations. He introduced an additional term, later known as the cosmological constant. This term acted as a subtle counterbalance to gravity, a gentle outward pressure that prevented the universe from collapsing inward. Mathematically, the solution worked. Philosophically, it felt necessary. For years, the static universe remained the accepted model. There was no direct observational evidence to challenge it, and Einstein's reputation gave the idea considerable authority. The cosmos appeared calm, balanced, and eternal, an unchanging backdrop to all physical processes. Yet this solution carried an underlying tension. The cosmological constant was not derived from deeper principles. It was added to satisfy expectation rather than observation. Quietly, it introduced an artificial symmetry into a theory otherwise praised for its elegance and inevitability. Einstein himself later expressed regret over this decision, describing it as a serious misstep. But at the time, the modification reflected a broader human instinct. When reality seems too strange, it is often reshaped to fit what feels reasonable. This assumption delayed a deeper realization. The universe was not required to remain still. It was capable of motion on the grandest possible scale. And soon, new observations would force science to confront that truth, whether it was ready or not. Even as general relativity gained recognition, its success did not mean every mystery had been resolved. While the theory worked beautifully in many situations, applying it to the entire universe exposed subtle inconsistencies that could not be ignored. The equations were powerful, but they depended heavily on assumptions that had not yet been tested by observation. One of the earliest confirmations came from the orbit of Mercury. Its slow shift over time had long resisted classical explanation, and Einstein's calculations matched the observed behavior with striking precision. This achievement strengthened confidence in the theory and suggested that spacetime curvature was not just an abstract idea, but a physical reality. However, when the same framework was extended to the cosmos as a whole, questions emerged. A universe governed entirely by gravity should not remain in perfect balance. Even with the cosmological constant in place, the stability of a static universe appeared fragile. Small disturbances could cause expansion or contraction, making long-term equilibrium unlikely. These issues were not immediately visible through telescopes. Instead, they arose from the mathematics itself. The equations hinted that the universe was more dynamic than previously imagined, even if direct evidence had not yet been found. The theory seemed to be pointing beyond the limits of current observation. At the same time, astronomers were improving their tools. Spectroscopy allowed light from distant objects to be analyzed in detail, revealing information about motion and composition. Although the implications were not yet fully understood, these techniques were quietly laying the groundwork for a major shift. What appeared to be a nearly complete theory was, in reality, unfinished. General relativity described gravity with extraordinary depth, but it also opened doors to questions it could not immediately answer. The universe was beginning to reveal that understanding its behavior would require not just better equations, but entirely new ways of observing the sky. As telescopes improved, astronomers began to realize that light carried far more information than simple brightness. By spreading light into its component colors, scientists could identify unique spectral patterns, distinct signatures produced by different elements. These patterns acted like fingerprints, revealing not only what stars were made of, but also how they were moving. A crucial discovery emerged from this analysis. When a light source moved toward an observer, its spectral lines shifted slightly toward shorter wavelengths. When it moved away, those same lines shifted toward longer wavelengths. This effect, later known as redshift and blue shift, provided a reliable method for measuring motion across vast distances. At first, these shifts were applied to nearby stars, confirming motions already suspected through classical observation. But when astronomers began examining distant nebulae, the results became far more surprising. Many of these objects showed strong redshifts, suggesting they were moving away at remarkable speeds. This raised an immediate question. Were these nebulae simply drifting through space, or was something larger at work? The speeds involved were far greater than anything expected within a stable, static universe. If these objects were truly racing away, then the long-held assumption of cosmic stillness was becoming increasingly difficult to defend. At the time, the true nature of these nebulae was still debated. Some believed they were clouds of gas within the Milky Way. Others suspected they were distant systems entirely separate from our own galaxy. The meaning of their redshift remained uncertain, but its presence could not be ignored. Light, once thought to merely illuminate the universe, had become a messenger of its behavior. Without changing the sky itself, observation had begun to reveal motion on a scale never before imagined. The universe was no longer just something to be mapped. It was something that was clearly, measurably, in motion. The debate over the nature of distant nebulae reached a turning point in the early 20th century. Using powerful new telescopes, astronomers were finally able to resolve individual stars within these faint objects. This observation carried enormous implications. If stars could be identified inside them, then these nebulae could not belong to the Milky Way alone. Edwin Hubble played a central role in this transformation. By measuring the brightness of specific variable stars, he determined that these objects were located far beyond the boundaries of our galaxy. The universe instantly became far larger than previously imagined. The Milky Way was no longer the entirety of existence, but only one galaxy among countless others. Hubble then connected this discovery with earlier measurements of redshift. When he compared the distances of galaxies with how strongly their light was shifted, a striking pattern emerged. The farther away a galaxy was, the faster it appeared to be moving away. This relationship was consistent and measurable, not random or isolated. The implication was unavoidable. The universe was expanding. This expansion did not suggest that galaxies were simply flying outward through empty space. Instead, space itself was stretching, carrying galaxies along with it. There was no central point of explosion, no preferred direction. Expansion occurred everywhere at once. This realization overturned centuries of assumption. The universe was not static, eternal, or fixed. It was dynamic, changing, and governed by processes that unfolded over immense spans of time. The cosmos now had a history. With a single discovery, the universe shifted from a timeless backdrop into an evolving system. And once motion was acknowledged on the largest scale possible, the question of origin could no longer be avoided. The discovery of cosmic expansion forced scientists to rethink what motion truly meant on the largest scales. At first glance, it was tempting to imagine galaxies rushing outward from a single point, like fragments from a colossal blast. But this image quickly proved misleading. In an expanding universe, galaxies are not moving through space in the usual sense. Instead, the space between them is stretching. Every region of the cosmos experiences this expansion equally, making it impossible to identify a central location. From any galaxy, all others appear to be moving away. The effect is not caused by propulsion, but by the changing geometry of space itself. This distinction was critical. It explained why expansion could occur without violating known laws of motion. Galaxies were not accelerating through a fixed background. The background itself was evolving. Distances increased because the fabric of the universe was growing over time. Understanding this concept required a shift in intuition. Everyday experience offers no direct comparison for expanding space. Yet mathematically, the idea followed naturally from general relativity. Once the assumption of a static universe was removed, expansion emerged as a simple and unavoidable solution. This new perspective also carried profound implications. If space had been expanding, then in the past it must have been smaller, denser, and hotter. The universe was not only changing, it had once been dramatically different from what it is today. Expansion transformed cosmology from a study of structure into a study of history. The universe could no longer be described solely by its present state. It had a past that could be traced and a future that could be predicted. Motion was no longer a local phenomenon limited to stars and galaxies. It was a property of the universe itself, and that realization set the stage for the most challenging question of all: how this expansion began. Once expansion was accepted as a fundamental property of the universe, scientists began asking a simple but unsettling question. If space is expanding today, what happens when that process is reversed? Running the cosmic clock backward led to an unavoidable conclusion: the universe must have been smaller in the past. As distances between galaxies shrink in reverse, matter becomes more tightly packed. Temperatures rise. Energy densities increase. The calm, structured universe observed today begins to dissolve into a far more extreme state. This was not speculation, but a direct consequence of the same equations that described expansion. Following this logic further revealed something remarkable. There appeared to be a moment when the universe was compressed into an unimaginably dense and hot condition. Space itself approached a limit where known physical laws could no longer fully describe what was happening. This point marked the edge of scientific certainty, not necessarily the beginning of everything, but the earliest state that physics could meaningfully explore. This realization changed the nature of cosmology. The universe was no longer eternal in its current form. It had a history that could be studied, reconstructed, and tested against observation. Questions about origin shifted from philosophy into the realm of science. Importantly, this idea did not claim to explain why the universe exists. It focused on how the universe evolved from an early, compact state into the vast structure seen today. Cause and purpose remained open questions, carefully separated from measurable processes. As models improved, predictions followed. An early hot universe would leave traces behind faint signals embedded in space itself. If such evidence could be found, the idea of a dense early state would move from theory toward confirmation. By tracing expansion backward, scientists had not yet solved the mystery of the universe's beginning. But they had discovered something equally powerful. The universe carries a memory of its own past, written into its structure, waiting to be read. The concept of an expanding universe led naturally to a bold proposal. If space, time, and matter were once compressed into an extremely dense state, then the universe may have emerged from a single primordial condition. This idea did not describe an explosion in space, but the expansion of space itself from an initial, compact phase. Georges Lemaitre was among the first to develop this perspective. Trained in physics and mathematics, he applied Einstein's equations without assuming a static universe. The result was clear. Expansion was not an anomaly, it was a prediction. Lemaitre suggested that the universe began as a primeval atom, a state in which all matter and energy were concentrated before expansion unfolded. At the time, this idea was met with skepticism. Many scientists were uncomfortable with the notion of a beginning. A universe with an origin seemed too closely tied to philosophical or theological implications, even though the proposal itself relied purely on mathematical reasoning and observation. Despite resistance, the model offered clear advantages. It explained expansion without artificial adjustments. It connected naturally with observed redshifts. Most importantly, it made testable predictions. An early dense universe should leave behind measurable effects, even after billions of years. Lemaitre's proposal did not attempt to describe the absolute start of existence. Instead, it defined the earliest phase that physics could address. Beyond that point, current theories simply ceased to apply. This careful distinction allowed the idea to remain within scientific boundaries. Gradually, the focus shifted from whether the universe had a beginning to whether evidence supported such a model. The answer would not come from philosophy, but from observation. And within a few decades, the universe itself would provide a signal that transformed this bold hypothesis into a central pillar of modern cosmology. If the universe began in a hot, dense state, it should have cooled as it expanded. As temperatures dropped, matter and radiation would eventually separate, allowing light to travel freely through space for the first time. That ancient light, stretched by billions of years of expansion, should still exist as a faint background filling the universe. For years, this idea remained theoretical. Then, in the mid-20th century, an unexpected discovery changed everything. While testing sensitive radio equipment, researchers detected a persistent, uniform signal coming from all directions in the sky. It could not be traced to stars, galaxies, or any known source of interference. This signal turned out to be relic radiation from the early universe. It was the cooled remnant of intense heat from a time when the cosmos was young, dense, and opaque. The universe itself was emitting a quiet echo of its earliest phase. The uniformity of this radiation was crucial. It appeared almost identical in every direction, suggesting that the early universe was remarkably smooth and evenly distributed. Small variations within this background hinted at the seeds of future structure regions that would later grow into galaxies and clusters. This discovery provided strong support for the idea of a hot early universe. Competing models that proposed an eternal, unchanging cosmos struggled to explain such a signal. The evidence was not philosophical or abstract. It was measurable, repeatable, and embedded in space itself. For the first time, cosmology had direct observational access to the universe's earliest chapter. The past was no longer inferred only through equations. It was being observed. With this faint signal, the idea of a primordial beginning moved from hypothesis to foundation. The universe had revealed a trace of its own origin, preserved across time, waiting until humanity had the tools to detect it. The success of the modern cosmological model answered many long-standing questions, but it also revealed the limits of current understanding. While observations support an expanding universe that evolved from a hot, dense early state, they do not explain everything. Some of the most fundamental questions remain open. At extreme conditions near the earliest moments, known laws of physics break down. Gravity, described by general relativity, cannot be fully reconciled with quantum mechanics. Without a unified framework, the true nature of the universe's earliest phase remains beyond precise description. There are also deeper questions about why the universe has the properties it does. Certain physical values appear finely balanced, allowing structure and complexity to form. Whether this balance is the result of deeper principles, chance among many possible universes, or something not yet understood is still debated. Some models suggest the universe may undergo cycles of expansion and contraction. Others propose that our universe is part of a much larger multiverse. These ideas extend current theories but remain difficult to test directly. They sit at the boundary between physics and speculation. Importantly, unanswered questions do not signal failure. They reflect the natural edge of scientific exploration. Each discovery reshapes the questions that follow, often revealing more complexity rather than final answers. The universe, once seen as static and eternal, is now understood as dynamic and evolving. Yet its ultimate origin, its long-term fate, and the reason its laws exist at all remain open mysteries. In this way, cosmology mirrors humanity's oldest impulse. Even as knowledge grows, curiosity endures. The universe continues to invite investigation not as a puzzle to be closed, but as a story still unfolding. From ancient myths carved into stone to equations written in modern laboratories, humanity's understanding of the universe has never stopped evolving. Each generation has inherited questions from the one before, adding new insights while uncovering new mysteries. What began as stories about gods and constellations has become a scientific journey through space, time, and the origins of reality itself. Yet despite centuries of progress, the universe has not lost its sense of wonder. If anything, it has grown more profound. The deeper we look, the more we realize that knowledge does not end curiosity, it fuels it. This story is not about having all the answers. It is about the human drive to ask better questions, to look beyond what is familiar, and to keep exploring even when certainty fades. Thank you for spending this time reflecting on the universe with us. If you enjoyed this journey, do not forget to follow the channel for more stories that explore history, science, and the mysteries that still shape our understanding of the world. Until next time.